Hello and welcome to a lesson on chemical kinetics, an introduction to collision theory. My name is Donald Goff. I'm happy to have you here this evening. The objectives of this lesson: students will perform a POGIL activity on introduction to collision theory. Students will use prior knowledge about light sticks to make predictions about consumption of reactants. Students will observe a light stick and sketch a Maxwell-Boltzmann distribution with threshold energy line to explain which particles can react. Students will conduct an experiment where light sticks are placed in water baths at different temperatures to determine the effect of temperature on rate. Students will sketch a potential energy diagram to relate activation energy to threshold energy. Students will sketch a catalyzed reaction path on the potential energy diagram and the threshold energy on a Maxwell-Boltzmann distribution. The prerequisites for this lesson: students should have already gone through the Maxwell-Boltzmann distribution, what one is. In my class, I actually do a POGIL activity on that as well. So students do that early in the year, as this is a fundamental, I think it's a foundational principle that we use to explain many things in chemistry. So we do Maxwell-Boltzmann distributions early. Also, students should have a background in kinetic and potential energy, at least understanding that kinetic energy is energy of motion and potential energy is stored energy. Also, students should have studied a unit on thermodynamics, especially the basics like exothermic and endothermic reactions. Students should have already learned how to draw potential energy diagrams, and also, as I usually demonstrate, a catalyzed decomposition of hydrogen peroxide, such as elephant toothpaste, which is hydrogen peroxide with potassium iodide, or genie in a bottle, which is much more rapid with potassium permanganate and hydrogen peroxide. So this is a picture of the POGIL activity. So the first thing in a POGIL activity I like to do is give a title, and then basically the essential question: do all collisions between particles result in a reaction? Then give it some type of background information so the students can begin. So that's the why statement. Some reactions, such as the explosive reaction of hydrogen gas reacting with oxygen gas, are very rapid. However, reactions like iron rusting are very slow. The branch of physical chemistry that is concerned with the reaction rate at which reactants are transformed into products is called chemical kinetics. Collision theory is used to help explain what is taking place during a chemical reaction and model factors that affect the rate of a reaction. The first big idea in collision theory is that particles must collide in order to react. And so usually in the first model it's something simple. In this case, this is a picture of some light sticks, just a sketch, and we all know that what happens when we snap and shake glow sticks. So the students would actually have a glow stick. This first one I would demonstrate for them. So I would walk around the class, allow the students to inspect the glow stick to see that there's a container inside the container. And so the first question is, why do you snap it? As long as the chemicals are inside the containers and they're not touching, then the chemicals will not react. So breaking the inside container will allow the chemicals to mix. Shaking them will help mix them rapidly, and so that's why we snap it. How long does it last? It would depend on the type of light stick. Sometimes I buy the large ones from Flynn, and those will last up to 12 hours. So sometimes I'll let the students read the package. So it depends on the light stick that you purchase. Is it always the same brightness? And the answer to that is, of course, no. It does dim over time. Consider a light stick that has been activated. Do all of the reactants, are all of the reactants used up in the first minute? Well, I've already done one of these in front of them at this point, and they can see that the light stick is still glowing. At this point, I usually explain to them that there's a reaction called chemiluminescence, and I tell them that the brightness has to do with, or how bright it is, has to do with how fast the reaction is taking place. And so that way they get a little background that that the brightness of the glow stick is correlating a little bit with the rate of reaction. And then I usually have the students fill in a circle, make a pie chart. How much do they think is consumed in the first 10 minutes? And so they would just make a simple pie chart. If they think 50% of the reactants are used up, then they would fill half of the circle in. But often it's just a very thin pie piece that the students fill in, especially if the light stick is expected to last up to 12 hours. And so a student may just come in here and shade in a very small piece of the pie. Okay, like that. Then the next thing we want to do is build a mental model. Most of the students will agree that not all of the reactants are used up right away. So what is it that prevents the unreacted portion from reacting? So the first thing we want to do then is to sketch the kinetic energy distribution of particles. This is also known as a Maxwell-Boltzmann distribution. Once again, this is something we would have done before. So we can start here, and in the directions it says, draw the curve representing a relatively low temperature, such as room temperature, and so we'll go ahead and attempt to draw this here. And so let's suppose we have something, and it approaches like that. Now it says, are there a lot of particles with high kinetic energy, or are there few particles with high kinetic energy? And of course, there are not many particles with high kinetic energy relative to the ones with the average kinetic energy. And so the next thing we would do is we would go ahead and indicate that the average correlates with a temperature. And so we would bring this line down, and we would call that the temperature 1. And this is something the students would do, but if they need guidance, we'll get around there to guide them. And then it says, mark the threshold energy by drawing a vertical line. This line represents the energy needed to break or bend bonds in order for the reaction to take place. And the reaction energy, let's suppose it's way out here. This is the threshold. And so we would actually indicate that on there, that this is the threshold. Threshold energy. I'll just abbreviate. All right. And so then it says, color in the particles that have enough energy to react. And so the students have to realize that you have to be beyond this line in order to react. And so only these number of particles can react here. So here's a picture that I got off the internet that shows something similar. It's a little cleaner than my drawing, but once again, there would be if they had a lower activation energy or lower threshold line or higher. Right now, I just want them to draw a threshold line, and it would be towards the far end, because not many of the particles are reacting at once, because this is going to last up to 12 hours depending on the light stick. All right, so then I have the students activate 2 light sticks. So everyone is given light sticks in their lab groups or their collaborative groups. And the first thing I want them to do is to predict what they will see when they place the light sticks in hot water, and they'll place another one in cold water. So they'll make a prediction here, and then I will have already prepared hot plates just because of the time of the class. So I will have had a hot plate with a beaker on it with some water, and usually we'll turn it up. I don't want the water to boil because the water boils. I have had a light stick pop, and then the luminol is all inside the beaker. However, I do want it warm, and so usually raise it up to about 70, 80 degrees Celsius. And then I do have another beaker out there with ice water, and so the students are able to put one light stick into an ice bath, and they put another one into the warm water, and then they write down their observations. It will take usually a minute or so for the light sticks to come to thermal equilibrium with the water bath, and then it'll be pretty obvious that the warm water bath is producing a much brighter glow, and that the light stick that is in the cold water bath or the ice bath is now beginning to dim. Using 2 different colors, add 2 curves to number 6. So if we go back to number 6, and it says one curve showing the chemicals at lower temperature and another at higher temperature, and so if they go back and they draw that, then what they would do is they would end up with a picture. Oh, this is just a picture of the glowing. So this is a picture of one that's in warm water, one in cold water, and then the other one is maybe at room temperature water as a control, if you have a third one. But what they would do is, going back, they would see, they would draw a different color. And so let's suppose the blue is the lower temperature and the red is the higher temperature. And so they would draw this over the top of the Maxwell-Boltzmann distribution that they did at room temperature. And what they would see is that because the higher temperature has a greater average kinetic energy, that the number of molecules that have enough energy to react has increased, and the one at the lower temperature has less particles that can react at that temperature. And so they start to see that that the number of molecules that have enough energy in collisions can determine the rate of reaction. Model 3 is a potential energy diagram. At this point, what we want to do is, the students should have already drawn a potential energy diagram before. I do have a video linked here that can help them draw this. But the first thing I want them to do is decide, is the light stick reaction, is it endothermic or is it exothermic? Once again, they should have had a background in endothermic and exothermic reactions. And since the light stick is giving off light, it is exothermic, which means that the reactants are going to be up here. We'll just put R for reactants. And the products will be down here somewhere at a lower energy. And in the reaction pathway, we would have something come up here showing that the first thing that has to happen is energy has to go into the system to cause the transition state to take place, and we call this distance, this energy from the reactants to the transition state, the activation energy for the forward reaction. And so so they would mark the transition state, sometimes called the activated complex, which exists on the diagram. and they would label as TS, and it is the highest energy transition. It's the highest energy state. So here's a picture from that video that I have linked there, and this is just a cutaway, so the students can actually use this to help them draw a potential energy diagram in case they have forgotten. So read this. Usually when I put a read this into my POGIL activities is to give additional information. In this case, energy is required to break chemical bonds. Once again, this should have been covered in thermodynamics when you're discussing thermochemistry. They should know that the breaking of bonds requires energy, and bond formation gives off energy. If molecules collide with enough kinetic energy, the force of the collision may break the bonds. At the instant that some bonds are breaking, other bonds are forming. This species is referred to as the transition state. Once the transition state exists, the reaction may proceed to form products or separate back into original reactants. So between the reactants and the products, there is an energy barrier. The energy needed to go from the reactants to the top of the barrier is called the activation energy. The particles get this energy by colliding into one another hard enough. They exchange their kinetic energy for potential energy. So bond energy, one thing that we cover in our thermochemistry or thermodynamics, is that bond energy is potential energy. And so the energy, the potential energy of bonds is broken by the collision, the kinetic energy in the molecules. Show how the kinetic energy diagram and potential energy diagram relate to one another, and the activation energy is the threshold energy of the Maxwell-Boltzmann distribution. Model 4 is the effect of a catalyst. So prior to this lesson, I would have demonstrated the hydrogen peroxide decomposition that would be catalyzed either by potassium iodide or potassium permanganate. And so they would have seen that catalyst will speed up a reaction. So now we want to understand how collision theory helps us to understand how the catalyst speeds up the reaction. And so using a different color, they would draw a curve on the potential energy diagram that they had already drawn for the catalyzed reaction. And I'll show you a picture of what that would look like in a second. But while I'm on the slide, the next thing they would do is draw the original kinetic energy diagram from number 6 for room temperature. So they would redraw that on this, and then including the threshold line. And then they would draw a new threshold energy line for a catalyzed reaction and color in the particles that have enough energy to react. And ultimately, the question is, do all collisions between reactant particles result in a chemical reaction? If no, why do some collisions not result in reaction? One thing I always like to point out to my students is that paper will burn, however, in the presence of oxygen. However, the paper on their desk is not on fire. So obviously there is a threshold energy that you must reach in order to cause a chemical reaction. And so here is a picture of the catalyzed activation energy versus the uncatalyzed activation energy. And so that's what they would have drawn on that potential energy diagram. And this is the this is the threshold energy for the catalyzed reaction versus the no catalyzed reaction. That the threshold energy is now less. Once again, it's explained that the catalyst offers a different pathway, different mechanism, and so the transition state has a lower activation energy. These are my resources. Thank you.